Hello everyone, good morning. Today we'll discuss on the geometry of matter. The understanding the architecture, geometry and efficiency of crystalline unit cells. Myself Anima Ghosh, Associate Professor of Physics. Today we are going to discuss the one of important concept of crystallography known as packing factor. Packing factor, or more specifically if we say the atomic packing factor. So we know that in solid materials atoms are arranged in a regular repeating pattern called crystal lattice. However, these atoms not completely fill at above space. There are always some empty gap between them. To understand the how efficiently the atom are packed within a crystal structure, we use the concept of atomic packing factor. It defined as the ratio of the volume of occupied by atom in a unit cell to the total volume of the unit cell. This concept will help us to compare different crystal structure and understand their properties such as the density and the stability. So first, how we will define the atomic this packing factor that that packing factor it is should p dot f, that it is small v divided by capital V. So small v is the volume occupied by the atoms in the unit cell and capital V is the total volume of the unit cell. So here from this ratio we can see that high atomic packing factor means the atoms are tightly packed. That means atoms are closely packed with very small unoccupied space, and low packing factor, this value means they are loosely packed. Atoms are closely packed with enormous unoccupied sphere. So we will say the atoms thus are hard sphere assumption. We assume that atoms are hard sphere. So we can see that one atom they are closely packed, and this is a hard sphere model. And if we see that in atomic side model, that we can see that atoms and they have their bonding. So this fundamental assumption underpin the calculation of atomic packing factor, treating atom as rigid, incompressible sphere that occupy a definite volume within the unit cell. So we will consider the few case studies we using this atomic cell calculation. So we'll first consider the simple cubic structure for analyzing this. The first case studies will be with the simple cubic structure. So the most fundamental building block used to understand the atomic packing math is the cubic structure. So first let us demonstrate the simple cubic atoms per unit cell. That we know that in a cubic cell of simple crystal lattice there are number of 8 there are 8 atoms at the 8 corner of the cell, and each corner of atom is shared by 8 adjoining unit cell, and the share of each corner atom to unit cell is 1 divided by 8 of an atom. So total number of atom per unit cell we can find out 8 corner. So 8 multiply with 1 by 8. So this will be equal to 1. So number of atoms per unit cell here is, so number of atoms per unit cell is 1. So now the find out the atomic radius and the coordination number of this simple cubic structure. So in simple cubic structure, which we have defined here in this left side, this diagram, that in this diagram we have here the simple cubic cell atoms in connect along with the edge of the unit cell. So we can see here that if A is this A, small a, this is the length of side of cubic cell. So it is a cubic cell, so all the sides will be the same, and the atoms touch along the cube edge, and these are the atoms you can see, and the nearest neighbor distance here, the r. So you can see that here this r and this r, so these two r basically is equal to a. So we can write it as that 2r, this basically a, so r is equal to a divided by 2. So the radius, atomic radius of simple cubic structure is a by 2. That is, the radius is equal to half of atomic lattice parameter or length of the side of cubic cell. So now coming to the coordination number. So here we have shown this diagram that to find out the coordination number. So you can see here that each corner atom touch 4 atoms in its horizontal plane. So if we just see this side, that each corner atoms, they are touched with the 4 atoms in its horizontal plane. So one vertically above and one vertically below. This means that there are 6 equally spaced nearest neighbor atoms, each at a distance a from the atom. Therefore, the coordination number is 6. Means, let's say here that each atom touch with 4 atoms in horizontal plane, and the 2 atom, one is vertical, means it is coming in this, that 4 atoms in horizontal plane, and 2 atoms, one is vertically above and one is vertically down. So 4 plus 1 plus 1, that means 6. So there are 6 equally spaced nearest neighbors atom, each at a distance a from the atom. So the coordination number is 6. So coordination number is equal to 6. So now we will find out the atomic packing factor for this cubic structure. So how to calculating the packing efficiency of simple cubic? That we know that packing factor, that is volume of all atoms in the unit cell, means the total number of atoms in unit cell, they are the volume of the all atoms which are in that unit cell and the total volume of unit cell. So we consider the atoms are volume of one atom as a sphere of volume. So sphere of volumes means we know that 4 by 3 pi r cube, where r is the radius. So here we seen that in just previous slides that the number of atoms in unit cell here 1. So we can see at 1 the total volume of all atoms in unit cell is 1 multiplied by this. So this is basically, and divided by unit cell volume, that means here we can see as Q. So packing factor is this. So if we just substitute that atomic radius, that A is equal to 2r, then packing factor we can find out for this structure is packing factor is equal to pi by 6, that is 0.52, that is 52%. So simple cubic structure is closely packed, and polonium is the only one element that exhibit this structure. So cubic structure is loosely packed. An example is the polonium is only one structure that exhibit this structure. So this is the packing factor of the simple cubic structure. So this is the case study of simple cubic. In following lectures, will we do the case studies of FCC and BCC structure. So thank you very much for watching the video. Thank you.